Ted Schultz, who is going to tell us all about the NASA Sounding Rocket program. This is the WRX-R rocket, and SuGRE-1 payload is going to be whereabouts on this?
It's living right up here.
Oh, it's the very top little bit.
That's right.
Okay, and this is a previous mission that you had, and you're going to use a lot of the technology that you developed for this one, put it into that.
That's right. I mean, you know, our program is small. We don't have a lot of people, and we don't actually get a huge amount of money, so we try to reuse stuff wherever we can. This payload has actually flown in various states almost 5 times now, and it started flying back in 2005, and it's been slowly upgraded with new detectors, new cameras, new bits, new sub-experiments, things like this as we go, and that helps us save money and lets us do cool new stuff all at the same time.
This is the Ogress payload.
That's right, and this flew in 2015. This rocket launched in White Sands, New Mexico, and White Sands, New Mexico, you probably can't, this picture may be hard to see. White Sands, New Mexico has a giant missile range. It's owned by the Navy and the Air Force. It's absolutely massive. It's almost, 150 kilometers long, and it's, almost 80 kilometers wide. So it's a huge amount of space. It's closed to the public, and they use it for all sorts of stuff. The Navy uses it to test missiles and bombs, and NASA actually uses it to launch a lot of the sounding rockets, particularly the ones that we want to get back. Ours are telescopes, and we usually want to get them back, so we usually fly with parachutes, and we want to fly somewhere where we can get it back. Now,
tell us what a sounding rocket is.
Okay, sure. So, a sounding rocket is basically a small rocket. Now, these do go into space, but they're what's called suborbital. And what that means is that, they go into space, but they don't have enough velocity to actually go into orbit, right? So these go way up. They're up as high as the International Space Station, but then they come right back down. So this is just like if you fired a really powerful gun basically straight up. It's a parabolic trajectory, and then they're going to come down and land. So the history of these is that, at some point, scientists sort of said, hey, we want to do some science. How, we want to have smaller rockets that don't cost as much. We want to do maybe niche science that can't be done anywhere else. How do we do that? So they start investigating that. Well, it turns out the Cold War was probably the best thing for the sounding rocket program ever because they built tons and tons of rocket motors.
Right. At
some point, the rocket motors were obsolete. The Navy didn't want them, so they gave them to NASA. So in fact, this is a picture of our sounding rocket on the launch rail right before the launch, our last launch. This is the first stage rocket motor. Now, this is a solid motor. This used to be on an anti-aircraft missile that was on a Navy ship.
Right.
They're from the 1960s.
They recycled
that's right. NASA basically, the Navy gave them all to NASA, like hundreds of these for free if they would store them. And now they're used for peacetime use, which I think is really cool.
That is good.
And so this is our first stage motor. This is our second stage motor. So our rockets are called a Black Grant 9, and that just basically is a configuration of the motors. We have 2, solid fuel, and then this is the rest of the experiment portion. Our telescope lives inside of this little box. Now, some of you might be wondering, why the heck is this, what's this white box? It's made of styrofoam, and it was there to basically keep our payload at the same temperature during the cold desert night.
Right.
It doesn't have active heating, but it just kind of helps keep the payload from getting cold in the desert night. They don't even take it off. They just launch the rocket. The fins just go through it, and you just get confetti made of styrofoam, and it's on fire, and it just gets obliterated. So this is where our telescope lived. And this is a computer-assisted design model of our telescope. So most of our stuff, we design it in the computer first, and then we send it off to a machine shop, and there a machinist, he or she will make all the, physically turn those computer files into physical parts. So we model it first, then we build it. So our part's in here.
How big is this?
Oh gosh, I mean, you can see I don't know, they're about 60, 70 feet tall. Now I know feet, right? Like you guys kind of use feet, but
we use
I don't
feet
know.
Only,
Yeah. So it's pretty big. You can see this. The people are tiny. So this is quite long. So this section here is the boost guidance section, and it has little fins. And what boost guidance does is it allows you to steer the missile while the engines are still burning. Why do you want to do that? You want to make sure that your missile is going to stay on the launch range, not leave the launch range and maybe hurt somebody, land on them or whatever. So It's gonna it might be hard to see, but this is a plot of the missile range, and these circles are the predicted impact point for our rocket.
Okay.
If the rocket is gonna leave the missile range, this little white thing is actually an explosive paddle. Now, unlike liquid rockets that you can like close the valves and turn the motors off, our motors, once they're lit, they are lit. They're burning,
Okay.
they are gonna burn until they're done burning. So what they do is, this is a little piece of explosive, and there's some person, we never get to meet that person, in some magical room at range control with a button that they hold down, and if they let go of it, this blows up, and it basically destroys the top end of the motor. And when that happens, the burning propellant...
And that's all to keep it within that range?
That's right. The burning propellant doesn't go out the nozzle anymore, it goes wherever it wants,
Okay.
and we don't get any thrust, and the rocket no longer starts going, if it was going sideways, it stops going sideways.
Okay.
And so hopefully, it stays on the missile range. They don't blow them up very often, but it has happened, and it's another safety feature to basically keep people who are not on the missile range safe. Above that, you have the attitude control system. This is not very pretty to look at. What it does is, since we're a telescope, we want to look at a particular place in the sky. How do you do that? Well, first off, you have a device in the telescope that can look at the sky and see the stars and see where you are, and that part's called the star tracker. So this is another part we don't have to design. We just say, hey, we want to point at Vela, which is a dead exploded star.
And then
The attitude control system, people go, I know where that is on this night at this time. Rocket goes up. The attitude control system actually has gas jets made that squirt argon gas. And once you're out in the vacuum of space, there's no resistance. So the gas jets fire, and it's just like a nozzle that you would squirt, on an air hose. It applies a force, and the rocket can actually move around and point wherever you need it to
exactly
point.
where you want it to point.
That's right.
And you're pointing out Vela.
That's right. And so, you point to that, the star tracker looks at the sky and says, yep, where we're supposed to be, cool. And then we start staring at our target. And then the last section above that is the nose cone. The nose cone pops off at some point, and underneath it is a can that holds the parachute. It's actually two parachutes. One is a drogue, which is, if you look that up on Wikipedia or whatever, a drogue chute is usually a little parachute that helps pull the big parachute out of its can.
Oh, okay.
So we actually kind of have two parachutes. And that all happens after we're falling back into the atmosphere.
So how long is it going to take you to get up into your...
Okay, this is a great question. This all happens so fast. It's just crazy. These rocket motors push so hard that if you were on board, you would die. I mean, the forces are stupid. They're like 17, 18 Gs. So everything on board has to be made really, really sturdily and robust. Otherwise, it'll break. We're already going the speed of a slow bullet just from the first motor. The second motor lights, and by the time the second motor burns out, you're going 2,000 meters per second. That's incredibly fast. That's faster than a bullet.
2,000.
And then you're just coasting the rest of the way. So, the second stage motor burns out at 40 seconds. Right? And then you're just going up and up and up and up. And it takes almost 265 seconds is when we hit our apogee, which is the highest point that we get away from the Earth.
So 265 seconds.
That's as high as you get.
That's as high as you get in 265 seconds. Wow. And how long has SuGRE-1 got to float its sculptures in that time?
SuGRE-1 is going to float its sculptures at the end, but that's going to be kind of neat because, after we do our science observation, we're going to pop those sort of right before we start tumbling back down in through the atmosphere. So they'll see some zero G. They might even see some interesting motions. I didn't mention this, but one of the last things they do before we start hitting the actual atmosphere, they tumble the rocket. They use the last little bit of gas in the attitude control system to kind of tumble the payload. You're thinking, why would you want to tumble it? Well, it's going to get hot. It's, re-entry heats things. The friction from the air is going to make it hot. If it comes down all on one part, that part is probably going to melt and get damaged and bad things. So they kind of tumble it and spin it. And that way the heat gets distributed all over the whole thing. The first stage isn't even bolted. It's like slipped into the second stage. And as soon as the first stage motor burns out, the drag from its fins just pulls it away, and it just falls down to the Earth.
Right.
This piece falls down, this doesn't ever get very high.
Yeah.
I was outside one time where I probably wasn't supposed to be, and you can hear this part coming down, and it's kind of eerie because it sounds like a freight train. You can't tell where it's coming from. It's this weird whooshing sound, locomotive sound, and then all of a sudden, up, maybe 500 meters up range, you see this whump, and it has landed on the ground.
How do you guys know where to stand that's safe?
I'm usually inside of there's a building called the block house, and that building has 4-foot thick concrete walls and windows you can't see through. Most of the personnel that are close are inside that building.
Okay.
Almost nobody is outside just
Right.
for safety reasons.
Yeah. This is part of this landing.
Yeah, so this is neat. So after we come down, we're going to hit the desert, and we know we're going to hit pretty hard, even though we have a big parachute. What they do is they put, this part's called the crush bumper. It kind of does exactly what it sounds like. It's a piece of honeycomb aluminum. Originally it was about this tall, and it hits the desert first on the bottom of the rocket, crunches, absorbs all that energy to help protect all the pieces of the rocket. And it's worked really well. So this one did its job. It's got some little bits of New Mexico grass in it and things like that, but it's a good souvenir now. So this is actually, this piece here is actually this piece. So we kept it as a nice souvenir.
Tell us what technology you're taking from this one and putting it
Yeah, I mean, there's a lot.
upgrading.
So, you know, the actual external, we call these the skins. I mean, these metal parts, we tested them to make sure they were good, and we're reusing them.
Oh.
Our last telescope had 2 channels. We're reusing an entire channel, so we're using the same mirrors, the same collimator. You know, a lot of everything that we can reuse, we do reuse. That's because it just saves so much money and time. But for this rocket, you know, it's still going to be a Black Grant 9, but since we're landing in the water, it's kind of neat. First off, we don't have to worry about the narrowness of the missile range. So they went ahead and got rid of boost guidance. So our rocket will come off the launch rail, and then it's just, you know, there's no active guidance. Whatever angle it comes off the launch rail is the angle that it's going. Now they do spin it. They have little spin motors that as soon as it exits the rail, they have these little rocket motors that kick it just to spin it a little bit like a bullet so that it's more stable.
Okay.
And it goes where it's supposed to go. We also don't have thrust termination anymore, so they're not going to be able to blow it up. So if it's going to go wildly off course, it just goes wildly off course. Now, the nice thing is, as you can see from this map, these are some islands in the Marshall Islands. Unless we're wildly out of place, we're not going to hit anything. We're going to be in the middle of the ocean, and everyone should be nice and safe. And again, there's an entire group at NASA that basically spends all their time analyzing this sort of thing, predicting the performance, just because, you know, you can't have anyone have rocket debris fall on. That would be very bad. So we don't have boost guidance, we don't have thrust termination, but what we do have on the bottom of ours, instead of a crush bumper, we have what's called the water wedge, which is this wedge-shaped piece that's going to break the surface of the water. Because if they think that if it just hit flat against the water, it would destroy the bottom part.
Massive belly flop.
Exactly. I mean, it's moving pretty fast, and water gets hard when you're moving fast enough. So they've got this water wedge. They actually have been testing it at Wallops by dropping it with a crane. It's very cool. It's new technology for them. They've never done that before. The other thing is how in the desert the rocket lands. You know, you got your parachutes, and it just sits there till you go get it.
Yeah.
In the water, it's a little more tricky. So they have float bags.
Right.
So they've got these giant inflatable things that are going to help keep it from sinking. They've got a dye pack that's going to like make the ocean orange so that you can see it from a helicopter.
Oh,
they have strobes, and they have I think it's a GPS receiver and an Iridium transceiver. So Iridium is like the satellite phone network. And so it's supposed to phone home as soon as it hits the water and say, I'm here, come get me.
Yeah, how quickly are you expecting that you will be able to?
Not fast, because the boat has to be outside. In White Sands, it's really trivial. The Navy sends a helicopter the next morning, and you just go fly out there. And they were able to track it with radar all the way to where it hits the desert. So you just literally fly out to it, right?
Yeah.
Now, sometimes they have to fly around because, you know, the missile range has lots of unexploded bombs from times long past.
Wow.
So sometimes they have to clear the area, but you just go get it. You just go pick it up. This is going to be tricky. I think their plan is to have a boat sitting way outside the area where it's predicted to land. As soon as they confirm that it hits the water, the boat's going to start chugging towards where it's going to land. Are you going
to have a helicopter as well?
They have talked about, it's going to be nighttime, and they've talked about having a search plane try to go find it. Now it's going to be hopefully phoning home as well and saying, hey, I'm here, you know, until the batteries go dead. So then the boat will come chug to it, and hopefully they'll load it on the boat, and then it takes, I guess, 2 days to get, I mean, the boats aren't fast, so it's going to take a while to get back to the island.
Are you guys going to be on load?
No, we weren't allowed. They said, no, we can't.
So you've got to sit there at the base, because the Marshall Islands is actually a military base, and you've got to just wait and hope.
Now we should have our data. Like, all of our data should be sit down, but the sugar payload, unfortunately, has to record all that stuff on board. So if we don't get it back, like, you know, that somewhere on the bottom of the ocean will be some really cool footage.
Oh no,
of...
shh.
Now, they recover telescopes from the water at Wallops Island, Virginia all the time.
Okay.
But these are much smaller rockets, and they're not telescopes usually. So they have some experience. So it's kind of an interesting back and forth between us, the experimenters, and them, the science, the NASA group, saying, hey, we really want to get it back. They say, we want to get it back too, but we are a little, we're a little bit nervous. But this is the first
with a telescope,
certainly with a telescope like ours that has been recovered. And I don't think they've been doing water recovery out of Swatch. Most of the rockets that launch out of there, they usually have another stage, and they don't give it back. They don't even have parachutes. They just go up, one-time use, sploosh, or they burn up. They go so high and so fast that when they come back through, they just get so hot that they just start melting and things like this. So ours is unique. We're pushing NASA to do something that they've never done. Why do we want to do that? Well, the southern hemisphere lets you have all sorts of targets and sky targets that you haven't had access to previously. And because you're launching in the middle of the ocean, you can actually lose some of these sections. Like, you don't need boost guidance, which helps us get longer. We want our telescope to be longer. So if we can get rid of some of these sections and put that length into our telescope, it makes our telescope work better. Yeah. So it's kind of this trade-off. So Kwajalein is neat. I've never been. I'm really excited. I've been to White Sands launching rockets. I've been to Alaska launching rockets, but I've never been to Kwaj. So I'm pretty excited.
It's going to be really
nice
and warm as well.
That's right.
So this is the mission logo for the WRX-R rocket. Yep. You might remember that we had a competition with the public to create our logo for SuGRE-1. And this is the logo for the whole rocket, which is the WRX-R rocket. Can you explain what these numbers are?
Yeah, okay. So because the sounding rocket program at NASA has they call them vehicles, and basically what that means is it's different combinations of engines or motors. Okay. They have different sizes, there are many different ones.
So that first number
is
the same as this
That's
one.
right, and that's because we are launching on what's called a Black Brant 9 configuration, which is a Terrier booster. This is the Terrier booster, this is the military surplus piece, and this is called a Black Brant, and that's our second stage. Those two motors stacked up like that, they just happen to call it a 36.
Okay.
This number is how many they've launched of that configuration. So we are the 330th rocket, which is kind of crazy, right? And nobody realizes that these things are launching all the time. There's almost 10, 15 per year, but nobody knows about it, really. It's kind of...
But you just found out, okay, you're number 300.
And that's right. And, our last one was 292. So between these two, 8 plus 30 have launched. So, 38 in about, 3-ish years. So, 10-ish per year.
Yeah. Who's this dude?
It's Poseidon.
Poseidon.
Yeah, so we kind of I don't know if you can see, our logo for Ogress had a female ogre kind of with the rocket over her shoulder, and she was ready to bash somebody with it. So we kind of like that. So we put Poseidon holding it this time because it's going into the water.
So how did you get into doing this?
Okay, so I was studying engineering at University of Colorado, and this was probably in 2001-ish. And I just happened to meet a guy. I was looking for a summer job.
What was your...
I was studying aerospace
subject?
Engineering.
Okay.
But I knew nothing of rockets, and I'd taken a few astronomy classes and kind of liked them, and I was looking for summer work. And I had actually asked my astronomy professor, hey, I'm looking for summer work. He's like, oh, I know this group. They're off campus, called the Center for Astrophysics and Space Astronomy, CASA. Send your resume to this guy, and maybe he can give you a job. So I sent my resume. I didn't hear anything. And I was just randomly in a lab, it was in the bottom of the planetarium for class, and I met this graduate student. I think he was TAing at the time, being a teaching assistant. And we started talking. He's asking me questions about, we kind of just hit it off, and I said, oh, I sent my resume out to, this place. He's like, really? He's like, I happen to work there. And so, like it always is, it's about who you end up randomly meeting sometimes. So this gentleman happened to be a grad student who was designing a rocket at the Center for Astrophysics. And I heard something back very shortly after that. I got a call and said, hey, come work for us. So I was just an undergrad. So the very first thing I did as an undergrad working on these rockets was not glorious engineering work, but it was kind of menial stuff, like I swept floors and
but you start
somewhere. So I basically started working as an undergraduate on sounding rockets, and I kept doing that and kept doing that.
Wow! So you literally started sweeping the floor for the people building.
That's right, and then eventually, as I proved that I wasn't completely foolish, I was given more responsibility. So maybe I started designing a few widgets for a rocket, or sometimes I was helping assemble things. And what's interesting is we have undergraduates in our lab now that are basically doing the role that I used to do, and now I mentor them, which is kind of
how
really
long
cool.
ago was that? So how long
2001.
Right, so you've been doing this for 16 years.
Yeah. And so, I worked on some rockets when I was an undergrad, and then I actually left academia, and I was in, I graduated, and I worked in the aircraft industry, so I was doing composite engineering, and I really didn't like it very much.
So you came back to
That's right. So I came back, and at the time I was, sort of broke and trying to find work, and it happened that Randy was getting a job offer to be a professor, and he says, hey, do you want to come help me set up this lab in Iowa and start a sounding rocket program? He's like, I think you probably know, since you've done it quite a bit, do you want to do that? And so I said yes, and that's sort of the rest is history. So I've worked on tons of payloads now, and I was shared between a couple different groups. So, I collaborated heavily with a group at University of Colorado that was doing, instead of X-ray telescopes, they were doing ultraviolet telescopes, and I worked on a couple of their payloads. Sometimes there's not enough work for a full-time engineer for an entire year, but you need somebody for half a year, so it actually worked out really well. I would get sort of passed around, and I would do electrical engineering for their rocket while I was doing electrical engineering for our rocket, and I worked on, let me think now. So I worked on, I'll try to name them all in order. One was called ISIS, which is not a good name anymore, but that was the one in 2001, and then I worked on its successor, and I can't remember the name of it, just a little bit. I worked on Randy's rocket, original thesis rocket, a little. It was called Success.
And you're the what guy? Like, what's your main...
These days, I am the only engineer in our group, so what I do is a little bit of everything poorly. So I do mechanical design, I do mostly electrical design, and mostly systems level electrical design. Well, what does that mean? So it's like, I'm the guy who's trying to figure out where people need to put connectors, and what size the connectors need to be, and where the wires are going to run, and if there's custom circuit boards, sometimes I get into those, but it's usually like sort of big picture stuff, like how is this all going to fit together, but mostly electronics engineering these days. I do dabble quite a bit in the CAD land, but it's mostly mentoring. The students are taking a huge load of that these days, so the students are actively involved in designing the parts, and I just sort of mentor them as
So you have undergrads working on
That's
this,
right, graduate students.
Postdocs, and people studying for PhDs.
Yeah, we have, right now there's basically 2 graduate students working on it. I'm the only actual engineer in our entire group. We've got Dr. James Tutt, who is basically doing somewhat, he's doing a little bit of engineering and a little bit of, science as well. So he's kind of sitting on that fringe. Did I say 2 graduate students? 2 graduate students, 3 undergrads. They're busy with class, but they come in and they work for a while, and then they go to class, and they get involved in almost everything. And of course, Randy is sort of, managing from on high, and Drew has a really interesting role. He's kind of getting an experience. He's trying to act as the project manager for the most part, which is unique because, not many students get to own a project of this scope when they're in graduate school. So he's trying to be the project manager and sort of keep all the various ins and outs moving forward. It's quite difficult.
Well, thank you. Thank
very
you,
welcome.
Ted. Thank you for taking us through this process.
It's a really exciting program, and it's really great. Students are heavily involved.
It's really exciting.
Yeah, on the space station, you can't do anything for less than like a gajillion $1 million. You can't go to the bathroom for less than like $5 million. So here, entire experiments that do amazing things are on the order of $1 million. And I know that sounds like a lot of money, but you can do amazing science for just and you can test things that you're not allowed to test because they're not proven, and that's weird. It's a catch-22. You can't launch the cool stuff until you've launched the cool stuff. Yeah. So we launch the cool stuff. It doesn't always work, but when it does, it's awesome.
But this one is going to
Oh yeah, it's going to be good. It's going to be good.
Excellent. Thank you.
You're very welcome.